Hi, good morning. So I am Stefano Petrarca, and I'm joined here by Ryan Wilkes, Brian Boveus, and Sam Dalco, and we are Team Teknor Apex here to present our project of heating and cooling control of extruder zones. So Teknor Apex expressed to us that their project motivation comes from the plastic extruders, and these machines are big dozen-foot long machines that are responsible for taking raw plastic filament and feeding it through a heated barrel that has a long screw going through it, and this screw is responsible for even mixture and approximately 70% of heating. And this melted plastic is passed through a die that is made by the customer specifications. The barrel is split up into different zones. Each zone is responsible for its own different heating conditions, but they all operate upwards of 400 degrees Fahrenheit. So over the 95 years Teknor Apex has been in service, they've made many generations of extruders that have been developed with different specifications, with different amount of zones, different architectures and CPUs, and just different interpretations of how this melting should be handled. This unfortunately has left them with a zone temperature variance of plus or minus 10 degrees Fahrenheit, and this can lead to problems such as difficulty of quality control from these products not being optimal, off-grade products with defects such as these and just burns that can lead to off-grade products, and all of these off-grade products lead to increased waste and increased costs because these can't be used. And I'm going to pass it over to Brian, who will talk about how we can resolve this.
Thanks, Stefano. Our best anticipated outcome for the project was to create an adaptable system to control the temperature of an extruder barrel and store historical data. Our key features include a streamlined user interface, accuracy to within 1 degree Fahrenheit, a database to store trend data, and a universal implementation on generations of equipment. Some broader implications and economic impact if we are successful with this project. For the extruders, it means a more consistent product and the ability to view historical trend data factory-wide and then prepare that data for machine learning. What this means for the company and industry is less waste, less product failures, more efficient production, and higher quality plastics, which in turn means millions in savings. Our general overview of the system we have in place is separated into two colors, indicated in blue for the CPE tasks and yellow for the ELE. Diving into our extruder zone, we have a single zone here with 2 holes in the middle for a dual screw to push the material through. These golden colored heating elements are 480 volts to heat the barrel. There's 4 of them to clamp around and create 2 full circles. This inlet right here is to pump water through to keep the barrel cool and to keep it from overheating. These holes around the perimeter just hook up to the next zone. For our wiring diagrams, we're using AutoCAD. AutoCAD lets us create an accurate representation by using product plugins, which are 2D wire drawings created by the manufacturers to represent their products, which we can just plug into our drawings. And I'm going to turn it over to Sam to talk about ladder logic.
Ladder logic is a programming language used to program the PLC, which then in turn controls the extruder. PLC stands for Programmable Logic Controller. So the control loop implemented within the ladder logic is called a PID and a PIDE. PID stands for proportional, integral, differential, and E stands for enhanced. Now the goal of this control loop is to hit your target temperature as fast as possible. You want to have as little overshoot as possible and then stay at said target temperature to create a critically damped system. So on the right, you can see how a PID is implemented in ladder logic. So our temperature simulation, which is one of our key accomplishments this semester, we have implemented a startup and stop sequence. We also have implemented variations in temperature to mimic real-world temperature disturbances and fluctuations. Now, something that interesting happens with an extruder is when it gets to 400 degrees, the plastic and the screw create enough friction that you no longer need heating. So now you add cooling. And cooling and heating take up different amounts of energy. So you get this back and forth fight of turning your heating and cooling on and off. This is an underdamped system. This is a huge waste of energy. So our hardest key accomplishment this semester, which is the highest difficulty, was to create a critically damped system with all said parameters of heating and cooling. And now, Ryan Wilkes.
And thank you. And a little bit more on ignition is what we control the PLC with, and essentially the extruder. As you can see, we use the operator touchscreen, and client users use the ignition. So basically, a little bit more about it is we use human-machine interface, which is basically the scheme to use to design the UI, which focuses on the operators and conveys data quickly to them so they know what's going on. A little bit about that. You want to avoid vivid colors like this here. We have a red, which is usually reserved for alarms especially, and only that. And so we want better scheme, so we stick with a gray scale. We have black here to show it's stopped, and white to show that it's running. Along with ignition is that we could store historical trends, and that's coming from all the tags from the PLC. So with that, we can make interactive graphs, and we could export them as PDFs to show trends and how to further tune the extruder. And along with ignition, there are alarms, like I said before, which those are going to use, red as a color. So the first one that we implemented was temperature, which is the most obvious one. You want to let the operator know that the extruder is overheating and it's going to ruin plastic. And then other things that are not so much known is that if the screw is overdrawing amperage, that it's going to cause damage to the motor. And so a little bit more about the remaining challenges is that the workbench setup was pretty hard to get actually set up. The zone itself is a couple 100 pounds, so that's a problem in itself. The heaters that we have shown they're 4 total, so they're around 16 kilowatts of heat energy, and they're also 40 volts, which is definitely pretty hard to set up in a school environment. But once we start that, we could get live data integration where we just take our simulations and apply it to the zone itself. And then later, after we get our PID and PID loops to work on the live data, we could switch over to pseudo-temperature interval control, which should give us a lot finer control over the temperature. And after that is completed, we could finalize our wiring diagrams to give to Teknor Apex, and then we could simulate a full ignition monitoring, where everything would be all 12 zones like it would be on the factory floor. These are our acknowledgments, and thank you very much for your time.